The universe appears calm and stable, a system where stars seem fixed in the sky for millions of years. In reality, space is a dynamic and often hostile environment, where processes of immense power occur continuously. Every star is a gigantic thermonuclear reactor, existing in a delicate balance between gravity and internal pressure. When this balance is disturbed, catastrophic events can occur, capable of affecting entire regions of space. From the perspective of astrophysics, the greatest threat to Earth does not come from hypothetical extraterrestrial civilizations, but from real cosmic objects, massive stars, unstable variables, gamma-ray burst sources, and even our own Sunday. These objects obey strict physical laws, and it is precisely these laws that make them potentially lethal. The Milky Way contains an estimated 200 to 400 billion stars. Many of them have already passed a significant portion of their evolutionary path. Stellar life is not eternal. All stars are born, change, and eventually die. Low-mass stars end their lives as white dwarfs, while massive stars explode as supernovae, releasing enormous amounts of energy, radiation, and subatomic particles. The energy released in a supernova explosion within a few seconds is comparable to what the Sun will emit over its entire lifetime of about 10 billion years. The resulting shock wave travels at thousands of kilometers per second, accompanied by intense gamma radiation and cosmic rays. If such an event occurs within 30 light-years of a planet with a developed biosphere, the consequences would be catastrophic. The ozone layer would be destroyed, the surface would be exposed to lethal ultraviolet radiation, and the global climate system would collapse. Even at a distance of 100 light-years, serious biological damage would be possible. Gamma-ray bursts represent an even greater danger. These phenomena occur during the collapse of massive stars or the merger of neutron stars. Their energy is released in narrow, relativistic jets. If one of these jets were directed toward Earth from within a few thousand light-years, the atmosphere could become heavily ionized, triggering a global extinction-level event. Modern science has indirect evidence that Earth has already been affected by such events. Traces of the radioactive isotope iron-60 have been found in deep ocean sediments. This isotope cannot form naturally on Earth and is considered evidence of a nearby supernova that occurred approximately 2 to 3 million years ago. Geological records also show abrupt climate changes and radiation anomalies that may be associated with the solar system passing through regions of increased stellar density within the galaxy. The solar system is not stationary. It orbits the center of the Milky Way at a speed of about 220 kilometers per second, completing one revolution every 230 million years. During this motion, it periodically crosses the galaxy's spiral arms, where massive and unstable stars are far more common. This means that the probability of nearby supernova explosions is not constant. At certain periods in Earth's history, our planet may have passed through zones of elevated risk, contributing to biological crises and mass extinctions. Human civilization has existed for only a few thousand years, an instant on cosmic timescales. During this brief period, no stellar catastrophe has directly affected Earth, creating the illusion of safety. However, astronomical observations show that dozens of potentially dangerous stars exist within a few thousand light-years of our planet, many of which are approaching the final stages of their evolution. The quiet universe is not peaceful. It is simply vast, and its true violence is hidden by distance and time. The closest star to Earth is also the most underestimated cosmic threat. The Sun is often perceived as a stable and eternal source of life, yet from an astrophysical perspective it is a highly active, evolving plasma system capable of producing destructive phenomena on planetary scales. At the center of the Sun, nuclear fusion converts hydrogen into helium, releasing energy that balances gravitational collapse. This balance, however, is not perfectly stable. The Sun undergoes continuous magnetic and plasma activity driven by convection and differential rotation. These processes twist and stretch magnetic field lines, storing enormous amounts of energy in the solar corona. When this energy is suddenly released, it produces solar flares and coronal mass ejections. A single major flare can release as much energy as billions of hydrogen bombs. Coronal mass ejections propel billions of tons of charged plasma into space at speeds exceeding 2,000 kilometers per second. If a large coronal mass ejection is directed toward Earth, it can severely disturb the planet's magnetosphere. The interaction between solar plasma and Earth's magnetic field can generate geomagnetic storms capable of damaging satellites, disrupting radio communication, and collapsing electrical power grids. Historical records show that such events are not theoretical. In 1859, the Carrington event caused telegraph systems across Europe and North America to fail, while auroras were visible near the equator. Modern technological infrastructure is far more vulnerable. A storm of similar magnitude today could cause global economic damage measured in trillions of dollars. Beyond technological effects, extreme solar activity can also affect the upper atmosphere. Increased ultraviolet and X-ray radiation can heat and expand the thermosphere, increasing atmospheric drag on satellites and accelerating orbital decay. The Sun itself is also evolving. In approximately 5 billion years, it will exhaust the hydrogen in its core and expand into a red giant. During this phase, the inner planets may be engulfed, and Earth's surface will become uninhabitable long before direct contact with the expanding solar envelope. Even in the near term, the Sun poses risks. Studies of solar analog stars show that stars similar to the Sun can produce super flares thousands of times more powerful than any recorded in human history. If such an event occurred on the Sun, it could strip parts of Earth's atmosphere and cause long-term climate disruption. Thus, the star that sustains all known life on Earth is also a source of existential risk. Its energy is essential, but its variability reminds us that even our nearest star is governed by the same violent physical laws as the most distant objects in the cosmos. Massive stars are the most violent stellar objects in the universe. Unlike stars like the Sun, which can remain stable for billions of years, massive stars burn their nuclear fuel at an extreme rate and live fast, unstable lives. Their masses range from 8 to more than 100 times the mass of the Sun, and their internal pressures and temperatures reach levels that drive rapid and unpredictable evolution. Because of their size, massive stars consume hydrogen, helium, and heavier elements in successive fusion stages. Each stage releases less energy than the previous one, forcing the star to burn fuel faster in order to resist gravitational collapse. In the final stages, the core is composed primarily of iron. Since iron fusion does not release energy, the star loses its internal support, and its core collapses in a fraction of a second. This collapse triggers a supernova explosion. The outer layers rebound from the compressed core and are ejected into space at speeds of tens of thousands of kilometers per second. During this brief moment, the star releases more energy than it did during its entire lifetime. The explosion synthesizes heavy elements such as gold, uranium, and lead, scattering them across interstellar space. For planets located nearby, a supernova is not a distant light show but a lethal event. The intense radiation pulse can ionize the upper atmosphere, destroy ozone, and expose the surface to high-energy ultraviolet radiation. The expanding shock wave carries cosmic rays capable of penetrating deep into the atmosphere, increasing mutation rates and disrupting biological systems. Astrophysical models indicate that a supernova within 30 light-years would likely cause a mass extinction on Earth. At distances of up to 100 light-years, long-term climate effects and increased radiation could still have severe consequences for life. Several massive stars in the Milky Way are considered potential future supernova progenitors. Among them are Betelgeuse in the constellation Orion, Antares in Scorpius, and Eta Carinae in the southern sky. These stars show signs of instability, including large-scale mass loss and dramatic brightness variations. Although these stars are currently hundreds or thousands of light-years away, their eventual explosions are inevitable on astronomical timescales. The exact moment cannot be predicted, but their existence demonstrates that supernova threats are not theoretical. They are a natural and unavoidable part of galactic evolution. The life cycles of massive stars illustrate a fundamental truth of astrophysics. The same processes that create the elements necessary for life also generate forces capable of destroying it. In the universe, creation and destruction are inseparable. Gamma-ray bursts are the most energetic electromagnetic events known in the universe. They occur when massive stars collapse into black holes or when compact objects such as neutron stars merge. In a matter of seconds, these events release more energy than the Sun will emit over its entire lifetime. Unlike supernovae, gamma-ray bursts do not radiate energy equally in all directions. Their power is concentrated into narrow, relativistic jets that travel at nearly the speed of light. If one of these jets is pointed toward a planet, the effects can be catastrophic even at distances of several thousand light-years. When gamma radiation enters a planetary atmosphere, it strips electrons from atoms, causing widespread ionization. This process rapidly destroys the ozone layer and allows lethal ultraviolet radiation from the host star to reach the surface. Within days, ecosystems dependent on photosynthesis would collapse, beginning a chain reaction leading to global extinction. Computer simulations show that a gamma-ray burst occurring within 6,000 light-years and directed at Earth could reduce ozone levels by more than 90%. Recovery would take decades, during which surface life would be exposed to extreme radiation levels. Evidence suggests that such events may have occurred in Earth's distant past. One hypothesis links a gamma-ray burst to the late Ordovician mass extinction approximately 445 million years ago, when a sudden loss of marine biodiversity coincided with climatic disruption and radiation stress. Gamma-ray bursts are rare on human timescales, but they are not rare in the life of a galaxy. In the Milky Way, several long-duration gamma-ray burst progenitors may exist among massive, rapidly rotating stars with low metallicity. Although no known gamma-ray source is currently aimed at Earth, the unpredictable nature of stellar evolution means that such a threat cannot be ruled out. Gamma-ray bursts represent the ultimate reminder that the most distant cosmic events can have immediate and devastating consequences for life on Earth. Although catastrophic stellar explosions are rare, the Milky Way contains several stars that are considered potentially dangerous due to their size, instability, and proximity. These objects are not immediate threats, but their physical properties place them among the most closely monitored stars in modern astronomy. One of the most famous is Betelgeuse, a red supergiant located approximately 550 light-years from Earth. Its diameter is so large that, if placed at the center of the solar system, it would extend beyond the orbit of Mars. Betelgeuse has already lost a significant fraction of its mass and shows irregular brightness variations, indicating that it is nearing the end of its life. When it explodes as a supernova, it will be visible from Earth even in daylight. At its current distance, however, it is not expected to cause direct biological damage. Another well-known candidate is Antares, a red supergiant about 600 light-years away. Like Betelgeuse, it is in an advanced evolutionary stage and undergoing strong stellar winds that expel vast amounts of material into space. While impressive, its distance reduces the likelihood of severe effects on Earth. Eta Carinae represents a different level of risk. This massive binary system, located around 7,500 light-years away, has already experienced a giant eruption in the 19th century, temporarily becoming one of the brightest stars in the sky. It is considered a likely future supernova or hypernova candidate. Because of its orientation, some models suggest that its gamma-ray jets would not be aimed toward Earth, but the system remains under close observation. Other potentially dangerous stars include Wolf-Rayet stars, which are extremely hot, massive objects shedding their outer layers at tremendous rates. These stars are often associated with gamma-ray burst progenitors and supernovae. The existence of these nearby massive stars demonstrates that Earth is not isolated from cosmic risk. While none of them pose an immediate threat, their presence confirms that destructive stellar events are an inevitable part of our galactic environment. The potential impact of a supernova on Earth depends critically on distance. Astronomers have established thresholds for various levels of biological and atmospheric consequences based on theoretical models and observational data. Understanding these thresholds is essential for assessing long-term planetary risk. A supernova occurring within 30 light-years of Earth would likely cause a mass extinction. At this distance, the combined effects of intense gamma radiation, X-rays, and high-energy particles would destroy the ozone layer within days. Ultraviolet radiation from the sun would penetrate the atmosphere without the usual protection, causing severe damage to DNA in living organisms, particularly those in shallow waters and terrestrial ecosystems. Ionization of the atmosphere could also trigger chemical reactions that increase nitrogen oxides, leading to acid rain and long-term climate changes. Supernovae between 30 and 100 light-years from Earth would produce significant but less catastrophic effects. The ozone layer would be partially depleted, resulting in elevated ultraviolet exposure over decades. High-energy cosmic rays would reach the surface, increasing mutation rates and potentially accelerating evolutionary pressures. Climate models indicate that global temperatures could fluctuate due to changes in atmospheric chemistry, affecting ecosystems worldwide. Beyond 100 light-years, supernova effects are primarily observational. The event would be extremely bright in the night sky, and its radiation would be largely absorbed by the atmosphere. However, gamma-ray bursts associated with supernovae, even at distances up to several thousand light-years, could still be highly destructive if their relativistic jets are oriented toward Earth. Historical evidence supports these models. Iron-60 deposits in deep ocean sediments indicate that one or more nearby supernovae occurred between 2 and 8 million years ago, likely within 100 light-years of Earth. While these events did not cause mass extinctions, they may have contributed to evolutionary pressures and minor climate perturbations. Monitoring nearby massive stars is crucial for estimating future risks. Observatories around the world, using both optical and gamma-ray telescopes, track brightness fluctuations, mass ejections, and other signs of instability. Computational models simulate the propagation of radiation and particle flux to evaluate potential damage to Earth's atmosphere and biosphere. Ultimately, supernova distance thresholds demonstrate that the universe, while mostly distant and empty to human perception, is capable of delivering sudden, catastrophic energy events. Even stars that are not immediately nearby can, under specific conditions, produce effects with planetary-scale consequences. Awareness of these thresholds provides both a scientific understanding of risk and a framework for long-term planetary defense strategies. Gamma-ray bursts, GRBs, are among the rarest yet most powerful cosmic phenomena. Unlike supernovae, which release energy isotropically, GRBs emit the majority of their energy in highly collimated relativistic jets. These jets can travel thousands of light-years, delivering concentrated doses of gamma radiation capable of devastating planetary environments. There are two main types of GRBs: long-duration bursts, typically associated with the collapse of massive, rapidly rotating stars into black holes, and short-duration bursts, usually resulting from the merger of neutron stars or neutron-star, black hole binaries. Long-duration GRBs can last from several seconds to minutes, while short bursts typically last less than 2 seconds but are often more intense. Estimating the frequency of GRBs that could threaten Earth involves combining observations with statistical models. Long-duration bursts are rare in the Milky Way. Current data suggest an occurrence rate of approximately 1 per million years per galaxy. Short-duration bursts may occur more frequently, but their probability of being pointed directly at Earth is extremely low due to the narrow angle of their relativistic jets. Despite the low probability, GRBs remain a significant concern because of their potential lethality. A long-duration GRB occurring within 6,000 light-years and oriented toward Earth could deplete the ozone layer by over 90%, leading to mass extinction events. Models also indicate that even at greater distances, such bursts could produce climate perturbations, destroy parts of the biosphere, and alter evolutionary trajectories. Geological evidence for past GRB events is limited but suggestive. Elevated levels of nitrates in ice cores and certain isotope anomalies in sediments have been proposed as indirect indicators of high-energy astrophysical events. These findings, while not definitive, support the plausibility that GRBs may have influenced Earth's biosphere in deep geological time. Astronomical surveys continue to monitor potential GRB progenitors. Wolf-Rayet stars, particularly those with rapid rotation and low metallicity, are prime candidates for long-duration bursts. Their location and orientation relative to Earth are carefully modeled to assess potential risk. Neutron star binaries are also catalogued, with their orbital decay and merger times projected over millions of years. Ultimately, gamma-ray bursts exemplify the unpredictable and distant threats posed by high-energy astrophysical phenomena. They highlight the need for a multidisciplinary approach combining astrophysics, geology, and atmospheric science to understand both the likelihood and potential consequences of these extreme events for life on Earth. Throughout Earth's geological history, evidence suggests that cosmic events have influenced the planet's biosphere. While asteroid impacts are the most widely recognized extraterrestrial hazards, high-energy stellar phenomena such as supernovae and gamma-ray bursts have also likely contributed to biological and environmental changes. One of the most direct lines of evidence comes from isotope anomalies in terrestrial and marine sediments. The detection of iron-60, a radioactive isotope with a half-life of approximately 2.6 million years, provides clear proof of nearby supernova explosions. Iron-60 cannot be produced in significant quantities by terrestrial processes, indicating an extraterrestrial origin. Samples from deep ocean ferromanganese crusts and lunar regolith confirm that supernova ejecta reached the Earth's surface approximately 2 to 3 million years ago. While no mass extinction coincided precisely with this event, minor disruptions in marine ecosystems may have resulted from increased cosmic radiation. Mass extinctions recorded in the fossil record sometimes show patterns consistent with potential cosmic influences. For example, the late Ordovician extinction around 445 million years ago involved a rapid loss of marine biodiversity and sudden climatic shifts. Some scientists hypothesize that a gamma-ray burst or nearby supernova could have contributed to ozone depletion, increased ultraviolet radiation, and subsequent biological stress, though definitive evidence remains elusive. Paleoclimatic records also provide indirect indicators. Sudden increases in nitrates and other isotopes associated with atmospheric ionization suggest that Earth's atmosphere occasionally experienced intense cosmic radiation. Tree rings and ice cores offer further, more recent evidence of heightened solar and cosmic activity, such as spikes in carbon-14 and beryllium-10 concentrations. These isotopes are produced when high-energy particles interact with the atmosphere, providing a natural record of past astrophysical events. Astronomical modeling complements geological findings. By simulating the trajectories and life cycles of nearby massive stars, scientists estimate the timing and potential intensity of radiation events impacting Earth. Such models suggest that during periods when the solar system passed through dense regions of the Milky Way's spiral arms, the probability of nearby supernovae increased significantly. These passages could have coincided with evolutionary pressures and shifts in global climate. While direct causal links between cosmic events and mass extinctions remain difficult to establish, the combined geological and astrophysical evidence demonstrates that the Earth's biosphere is not isolated from stellar processes. High-energy phenomena, even at distances of several hundred light-years, have the potential to alter atmospheric chemistry, climate systems, and biological evolution. Historical evidence thus underscores the reality of cosmic hazards. It confirms that the universe is not merely a passive backdrop to life on Earth but an active environment capable of influencing the trajectory of evolution and survival. Understanding these past events provides context for current scientific assessments of potential stellar threats and informs long-term considerations for planetary defense. Stellar remnants are the endpoints of stellar evolution and represent some of the densest and most energetic objects in the universe. These remnants, including neutron stars, white dwarfs, and black holes, can have profound implications for their surroundings and, under certain conditions, for planets located at great distances. Neutron stars form when massive stars exhaust their nuclear fuel and undergo core collapse. The resulting object is incredibly dense, a mass greater than that of the Sun compressed into a sphere only about 10 to 20 kilometers in diameter. Neutron stars often rotate rapidly, producing intense magnetic fields that can exceed 1 trillion times the strength of Earth's magnetic field. When these objects emit beams of radiation along their magnetic poles, they are observed as pulsars. While pulsars do not directly threaten Earth under normal circumstances, Their high-energy emissions demonstrate the extreme physical conditions possible in stellar remnants. White dwarfs, on the other hand, are the remnants of low to intermediate mass stars. They no longer undergo nuclear fusion and gradually cool over billions of years. However, in binary systems, white dwarfs can accrete matter from a companion star. If the mass exceeds a critical limit known as the Chandrasekhar limit, approximately 1.4 solar masses, the white dwarf can undergo a thermonuclear explosion as a type Ia supernova. These events release energy equivalent to the total output of billions of suns and are capable of affecting planets over distances of tens to hundreds of light years. Black holes, the remnants of the most massive stars, represent regions of space where gravity is so strong that not even light can escape. Although their effects are generally confined to their immediate surroundings, they can influence nearby stars, accretion disks, and high-energy jets. Relativistic jets from black hole systems, particularly those in active galactic nuclei, can extend for thousands of light years and potentially contribute to localized cosmic radiation hazards. The presence of these stellar remnants in the Milky Way emphasizes that the life cycle of stars does not conclude harmlessly. High-energy phenomena associated with remnants, such as pulsar winds, supernova explosions from white dwarfs, and relativistic jets, continuously reshape the galactic environment. For Earth, the primary concern arises from supernovae originating from white dwarfs in nearby binary systems and from gamma-ray bursts associated with rapidly rotating neutron stars or collapsars. Astronomical surveys focus on identifying and cataloging these remnants, measuring their distances, rotation rates, magnetic fields, and potential for high-energy emissions. Understanding the physical properties of stellar remnants enables scientists to estimate the probability and intensity of events that could impact Earth, providing essential data for planetary risk assessments. The study of stellar remnants illustrates a central principle of astrophysics. The death of a star is not the end of its influence. Instead, these objects become persistent sources of extreme energy, capable of shaping both their immediate stellar neighborhood and, in rare cases, affecting life on distant planets. Planetary vulnerability to stellar events depends on multiple factors, including distance from the energetic source, atmospheric composition, magnetic field strength, and the presence of protective layers such as ozone. While stars are essential for sustaining life, their energetic phenomena can pose significant risks to planets within a certain radius. One of the most critical factors is the planet's distance from the star. For supernovae, modeling indicates that planets within approximately 30 light-years are at high risk of mass extinction-level events. At distances of 30 to 100 light-years, partial ozone depletion and increased cosmic radiation can lead to ecological disruption. Beyond 100 light-years, direct biological effects are minimal, although high-energy phenomena like gamma-ray bursts can still pose risks due to the collimated nature of their emissions. Atmospheric composition plays a crucial role in mitigating or amplifying damage. Earth's atmosphere, with its oxygen-rich layer and ozone shield, absorbs a large fraction of incoming high-energy radiation. However, intense gamma rays and X-rays from nearby supernovae or gamma-ray bursts can ionize the atmosphere, breaking down ozone and increasing the penetration of ultraviolet radiation. Planets lacking a substantial atmosphere or ozone layer would be far more exposed to the destructive effects of stellar radiation. Planetary magnetic fields provide additional protection by deflecting charged particles from solar wind, supernova ejecta, and gamma-ray bursts. A strong magnetosphere reduces atmospheric erosion and surface radiation. Earth's geomagnetic field is crucial in shielding the biosphere, whereas planets with weak or absent magnetic fields, such as Mars, are far more susceptible to atmospheric stripping and radiation damage. The orientation and intensity of stellar events also influence planetary vulnerability. Gamma-ray bursts, for example, emit radiation primarily in narrow relativistic jets. A planet must be aligned with the jet's axis to experience full impact. Conversely, supernova explosions release energy more isotropically, affecting all planets within a critical distance. Biological complexity and ecosystem structure further determine vulnerability. Microbial life is more resistant to radiation than multicellular organisms, which rely on DNA repair mechanisms and protective habitats. Ozone depletion can selectively damage surface-dwelling and photosynthetic organisms, potentially causing cascading ecological effects. Historical analysis of Earth's biosphere demonstrates that planetary systems can withstand moderate stellar events, but repeated or extreme exposures may trigger mass extinctions. This highlights the importance of understanding both the frequency of high-energy astrophysical phenomena and the resilience of planetary systems. In conclusion, planetary vulnerability to stellar events is a multidimensional problem, governed by astrophysical, geophysical, and biological factors. Evaluating these parameters allows scientists to quantify the risks posed by supernovae, gamma-ray bursts, and other high-energy stellar phenomena, providing a framework for assessing long-term planetary survival in a dynamic and potentially hostile universe. Monitoring and predicting stellar threats is a critical component of modern astrophysics. Given the potential catastrophic effects of supernovae, gamma-ray bursts, and other high-energy phenomena, astronomers employ multiple observational techniques, computational models, and satellite-based systems to assess risk and improve preparedness. Ground-based telescopes provide continuous monitoring of nearby stars, particularly massive stars in late evolutionary stages. Optical, infrared, and radio observations track changes in luminosity, spectral lines, and mass loss events. Variability in brightness can indicate instability, while spectral analysis reveals changes in chemical composition and surface temperature, both of which are precursors to catastrophic events such as supernovae. Space-based observatories complement ground-based monitoring. Satellites equipped with X-ray and gamma-ray detectors, such as NASA's SWIFT and Fermi missions, observe high-energy phenomena that cannot penetrate Earth's atmosphere. These instruments detect gamma-ray bursts, solar flares, and other energetic outbursts in real time, providing essential data for modeling potential impacts on Earth and nearby planetary systems. Computational astrophysics plays a central role in predicting stellar threats. Models simulate stellar evolution, nuclear fusion rates, magnetic field dynamics, and core collapse scenarios. By inputting observed parameters of nearby stars, scientists can estimate timelines for supernova events, gamma-ray bursts, and other high-energy emissions. Probabilistic modeling accounts for uncertainties in distance, orientation, and energy output, generating risk assessments with quantified likelihoods of planetary impact. The identification of potential gamma-ray burst progenitors is a particular focus. Rapidly rotating, low-metallicity Wolf-Rayet stars are monitored for signs of core instability and jet formation. Neutron star binaries are studied to estimate merger times and the potential direction of relativistic jets. These analyses help define the subset of cosmic events that could produce life-threatening radiation on Earth. Data integration from multiple observational platforms allows scientists to create a dynamic map of potential stellar threats within the Milky Way. Combined with historical geological evidence and modeling of cosmic radiation propagation, these maps provide insight into both short-term and long-term planetary risk. Alerts for imminent events, such as nearby supernova precursors, can inform space mission planning, satellite shielding, and other protective measures. While the probability of a catastrophic stellar event impacting Earth in the near future is low, the consequences would be severe enough to justify sustained monitoring. Understanding stellar threats also advances broader scientific knowledge, including the life cycles of massive stars, the dynamics of high-energy astrophysical processes, and the evolution of galaxies. In summary, monitoring and predicting stellar threats integrates observational astronomy, space-based detection, and computational modeling to assess and mitigate the risks posed by the universe's most energetic phenomena. This approach exemplifies the proactive application of science to understand and prepare for rare but potentially civilization-threatening cosmic events. Preparing for cosmic threats and ensuring the long-term survival of life on Earth require a combination of scientific understanding, technological capability, and strategic planning. While the probability of a nearby supernova, gamma-ray burst, or other catastrophic stellar event affecting Earth in the immediate future is low, the potential consequences are sufficiently severe to justify proactive measures. One approach to mitigation focuses on continuous observation and early warning systems. By monitoring high-risk stars, stellar remnants, and other energetic phenomena, astronomers can identify precursors to potentially hazardous events. Early detection provides critical time to assess the likely impact and implement protective measures for satellites, spacecraft, and critical infrastructure. Space-based shielding and hardening of technological assets represent practical solutions for protecting human systems. Satellites can be equipped with radiation-resistant components and placed in orbits that minimize exposure to charged particles from solar and cosmic events. Power grids and communication networks on Earth can incorporate redundant systems and surge protection to withstand geomagnetic storms caused by solar flares or coronal mass ejections. Long-term strategies consider planetary and biological resilience. Understanding how high-energy radiation interacts with the atmosphere, magnetic field, and biosphere informs climate and ecological models, allowing scientists to estimate recovery times and potential evolutionary impacts. Research into radioprotective materials and biological adaptation could improve survival prospects in the event of extreme radiation exposure. International collaboration is essential. Cosmic threats are global in nature, and mitigating them requires coordinated monitoring, data sharing, and response planning. Agencies such as NASA, ESA, and other national observatories collaborate to track potentially dangerous stars, model high-energy events, and communicate findings to governments and scientific communities. Education and public awareness also play a role. While cosmic events occur on timescales far exceeding human lifespans, understanding the universe's dynamic nature helps societies appreciate both the fragility and resilience of life. It also emphasizes the importance of continued investment in scientific research and space observation. Finally, studying cosmic threats drives scientific and technological advancement. Efforts to understand stellar evolution, gamma-ray bursts, and supernova mechanisms expand fundamental knowledge of physics, chemistry, and astrophysics. They also inform the design of spacecraft, detection instruments, and planetary defense systems, with applications beyond immediate threat mitigation. In conclusion, the universe is both the source of life-sustaining energy and a potential origin of catastrophic forces. Preparing for stellar threats requires a multidimensional approach integrating observation, technology, ecological modeling, international cooperation, and public education. While complete protection from cosmic events is currently beyond human capability, understanding the mechanisms, probabilities, and consequences of these phenomena provides the foundation for informed strategies that maximize planetary resilience and the long-term survival of life on Earth.